We present a case study on a real residence in Brookline owned by Matthew C. Williams. Mr. Williams owns a 2-story, 4-bedroom, 2.5-bathroom, 2,500 square foot house featuring a finished basement and double bay garage. The house is surrounded by gardens, including an in-ground pool. Mr. Williams' house is heated by propane baseboard heat and a wood stove. Mr. Williams is concerned about using fossil fuels. Our solution not only reduces his monthly energy bill by over 40%, but also could heat his pool in the winter and melt driveway snow.
Our first thought was wind, because since the 1990s, wind energy is the world's fastest growing source of energy. Siting is important because the amount of energy in wind is proportional to the cube of the wind speed. Unfortunately, when we looked at the maps, the average wind speed in Brookline is below the 11-mile-per-hour range required to be effective.
Don Edson suggested geothermal. A heat pump, the heart of the geothermal system, is an electrical device that extracts heat from one place and transfers it to another. Window air conditioners and refrigerators are heat pumps. There are 3 basic principles of physics you need to know to understand how a heat pump works. First, heat flows from hot objects to cold objects. Second, much more energy is needed to convert liquid to gas and to raise the temperature of a liquid. This energy, the latent, is released when the gas condenses. To raise a pound of water from freezing to boiling temperatures, we need to add 180 BTUs. To convert 1 pound of boiling water to steam, we need to add 970 BTUs. That's the latent heat. Third, increasing pressure increases the boiling point. At normal temperature and pressure, water boils at 212 degrees Fahrenheit. Double the pressure and it boils around 250. At normal temperature and pressure, refrigerants are gases with a very low boiling point, but compressed refrigerants are liquid with a high boiling point. When the pressure is released, the liquid reverts to a gas, absorbing energy from its surroundings. Geothermal systems transfer heat from deep wells because a few feet below the ground temperature is always at 55 degrees Fahrenheit.
With those basic physics concepts, we can explain the components of a heat pump. Number 1. Well water heats or cools to earth temperature. Number 2. The evaporator adds energy equal to the latent heat to the refrigerant, converting it into a gas. Number 3. The compressor makes a warm, high-pressure gas from a low-pressure gas refrigerant. Number 4. In the condenser, latent heat is released as the refrigerant becomes a liquid. Number 5. Heat produced can be used for space heating. Number 6. The expansion valve cools the refrigerant.
Gary Meidel gave us a tour of the Broad Street Country Store geothermal system.
This is a forced hot air system.
Hot or cold water is ducted to fan coil units, where it conditions air blown into the room.
Now this building is about 10,000 square feet, but it also has a lot of volume. It takes about 16 tons of cooling to keep it cool, but the heating load on it is nominal. In this building, the geothermal is not only doing the heating and cooling, it's also doing all the refrigeration. You want to see how cold it gets? The thing's -5.
Oh, I love that. Like ice cream in there. I like
Well, it is.
You can just stay in there forever. Smell like ice cream.
There's a lot of refrigeration. This is the heat pump that does all the work. This is for the cheese coolers, which are out front. This is for the first floor freezer. This is for the other cheese coolers. This is for the produce cooling. So what's happening is the well water is coming in from the well, and it comes in to this black coil right here. It's a tube in a tube. The water is on the inside. On the outside of that is Freon.
Over pizza, we learned enough to estimate the cost for converting Mr. Williams' house. The heat requirements for 2,500 square feet are 5 tons. That's 17.58 kilowatt hours. The well needs to be 100 feet to 200 feet per ton. Retrofitting baseboard heat and installing a system for 2,500 square feet costs $12,500 to $17,000.
For every $4 of heat moved, it takes $1 of electricity to operate the pumps and compressors. Is there a substantial source for that electricity? Many believe foggy New England won't benefit from solar.
You have more Sundays here than most parts of the country. It's approaching 300 days a year.
Really?
Well, yeah.
We get 30% more Germany or Japan.
There's a small microclimate here, which is like from here to probably exit 12 and probably the other side of Chelmsford. And it goes out to Pepperell and I think as far as maybe Wyndham.
We suggest installing Grow Solar's UT 2,520, providing an average of monthly 244 kilowatt hours, requiring 225 square feet of roof space. The 14 panels would produce about 15% of his current electricity use.
Summarizing our solution, Mr. Williams' current maximum need is 70 kilowatt hours per day.
We use data from the Department of Energy and PSNH to estimate his costs. He currently spends about $5,000 per year for energy.
The constantly running refrigerators, freezers, and the sporadic use of spa pump and heater are a big part of his electricity use.
Replacing these items with geothermal-based alternatives will reduce his electricity use by 66%.
Without the need for propane and plowing, his annual energy costs will be about $553.
We estimate the project will cost about $40,000 to $45,000.
We offer incentives for customers to use geothermal in existing homes and in new construction. We look to pay for about half the cost.
Incentives are available. The system will pay for itself and increase the value of his home. Mr. Williams will enjoy his pool and spa all year and be plowed out from snow and air quality improved. He'll have peace of mind knowing he uses very little fossil fuels for his home energy.